So thanks a lot, Sven, for the intro, and thanks to James and Patricia and Sven for putting this this series together and for inviting me to talk about some of our recent work. So I'll be telling you about a couple of structures that we solved of the formate hydrogen lyase complex from E. coli. And before I kind of get into it, I want to introduce Ralf Steinhöper, who's the PhD student who's been working on this project. He's put a lot of kind of a lot of talent, but also a lot of heart into this project. And so, and he's done a really great job. So FHL is a little bit like, I don't know, an old love of this community, I suppose, because already at the beginning of the 20th century, Pakes and Jollyman were looking at bacterial fermentation and noticed that formate could be converted into CO2 and H2 by cultures of bacteria that later turned out to be E. coli. And that was the activity of this complex, the formate hydrogen lyase complex. And it sort of remained a topic of interest for a number of groups over the years. Stevenson and Stickland in the 30s, and August Book and his colleagues, and much more recently, Gary Sawyers and Frank Sargent, among others. And so this has been a sort of, a long but sort of tough lover for, I think, quite a few people. In spite of the fact that people have been working on this complex for over 120 years, the first time that it was isolated in an intact or active form was only within the last decade. And that was done by Frank Sargent by introducing an affinity tag into the large hydrogenase subunit, an internal affinity tag on the chromosomal copy of the complex. And we were really glad to be right along with Frank in this project. And so in my PhD, I got to characterize the activity of the hydrogenase 3, so the hydrogenase that's part of this formate hydrogen lyase complex. And what we saw by PFV immediately was that it's quite a good hydrogen producer, which wasn't surprising given its role in vivo. But what did surprise us a little bit was when we looked at the inhibition of hydrogen production by hydrogen, so the product inhibition of H2 evolution. Hy3 really stuck out relative to other nickel iron hydrogenases and even nickel iron selenium hydrogenases, and had a much higher Ki, more similar to iron hydrogenases. So that is something that makes this complex quite interesting, and we can talk a little bit more about that. Another reason for interest was kind of developed a little bit more in Frank Sargent's group by Magali Roger and colleagues, where they pressurized cultures of E. coli and showed that actually E. coli can be quite an efficient whole cell catalyst for converting H2 and CO2 to formate, so running in the opposite direction and carrying out hydrogen-driven CO2 reduction. And a third reason that we're quite interested in FHL is its homology to complex 1. So all of the subunits of FHL are homologous to subunits of complex 1 and the other relatives in the complex 1 superfamily. So those are kind of the things that drove us to be interested in getting a structure for this complex. But of course, since it was only recently isolated, there are a few bumps along the road. And so when Ralph started working on this project, we were already quite happy to see something coming out of our column. And we actually quite quickly turned to our collaborators in Marburg, Johann Haider and Gabi Höf, who works in his lab. And they helped us out by doing a really large scale anaerobic fermentation of the E. coli and an anaerobic harvesting. And that allowed us to then kind of move forward with the purification. And in the first case, coming off of the nickel column and then off of an SEC, we had 2 peaks. And so we could see that the first peak looked quite good, and the second peak was missing the membrane-bound subunits. So we went about kind of trying to solve the structure. And I can show you just the overall, quite quickly we were able to see the overall kind of layout of the complex, if you will. So at the top with the orange subunit, we have the formate dehydrogenase. That's where formate is oxidized to CO2, and electrons are then passed from the formate down a chain of iron sulfur clusters to a nickel iron cofactor. But when we looked at this nickel iron cofactor and we're building the model, we noticed quite quickly that we were short some density. So we had very little density for the nickel iron cluster and very little for the proximal iron cluster. And so given that this complex is expressed under anaerobic conditions, our first guess was this was probably breaking down due to oxygen exposure. And so Ralph took his project into the tent. This is our anaerobic tent where we have an FPLC, but also a Vitrobot. So that allows us to go all the way to the stage of preparing grids for cryo-EM analysis without seeing oxygen. And we were really pleased to see this peak on the SEC that no longer was losing these membrane subunits, but looked to be intact. But when Ralph solved the structure of this complex, he noticed that the proximal cluster and the nickel iron catalytic site were intact and they looked really good. And the density around them was also better ordered, but we were missing this FDHF subunit completely. So this is where, you know, the love affair gets a bit tempestuous because you start to sort of think, oh, but the map was really well resolved. So we were able to build in some lipids, including also a cardiolipin here that's kind of being embraced by the antiporter-like subunit HIC-C. And in addition, oh, sorry, now I'm just trying to, so you can see here the cardiolipin sits inside the C-terminal part of the antiporter-like subunit. And in addition to that, we could also resolve a set of loops that lie at the interface between the membrane arm and the soluble arm of the FHL complex. And these loops have been observed to be relatively flexible in complex 1 relatives and seem to be important for the process of coupling turnover at the active site with ion translocation across the membrane. So these were all nicely resolved in our anaerobic structure, and so that gave us some confidence that we were looking at something something worthwhile, let's say. So just to kind of sum up, although the resolution was better and the clusters were intact, the things that were most interesting for us were we saw these loops better ordered in the anaerobic structure, and we think that that's related to retaining these membrane subunits. So we think that the disorder caused in the loops by breakdown of the nickel iron catalytic subunit might be the reason that the membrane subunits fall off so easily. But we had no subclass of particles containing the FDHF. We also, of course, tested the activity, and we were happy to find that the activity of the anaerobically prepared enzyme was more than 20 times higher than our aerobic prep. So that was good confirmation that we were looking at the right thing. And moving forward, I'll just mostly talk about the anaerobically determined structure, except where I talk about the attachment of the FDHF. So I've mentioned the different subunits. We have the large subunit in pink and the blue the small subunit in blue and the formate dehydrogenase on top. And down in the membrane, we have a subunit that's homologous to the ND1 subunit of complex 1. And then some people call that the universal adapter. And then we have an antiporter-like subunit. And what's apparent when you look at the model relative to complex 1 is if you align them on the basis of the antiporter-like subunit, the whole rest of the complex has actually shifted to the other side of the antiporter. So this is complex 1 and FHL aligned on the basis of the antiporter-like subunit, and the whole rest of the complex is shifted to the other side. And this was already observed by Michael Adams and Huilin Li with the MBH of Pyrococcus, and as well as the related MBS complex. But it's kind of, I think it's a really fascinating observation. We don't quite know what it means yet, but what we do know is that then this mechanism of coupling turnover at the catalytic site to proton translocation across the membrane is somehow simple enough that it persists even when you have this really large scale architectural arrangement. So quite an interesting thing. And when we look a little bit more closely at the cofactors in the complex, we have the molybdopterin site that we expect and a chain of 4 iron 4 sulfur clusters. But we also had an ion that we didn't expect to see, and that's coordinated by a set of 4 cysteines in the C-terminus of HIC-F. And at first we kind of thought, okay, you know, structural or something like that. But as Ralph worked more and more to try to get the structure anaerobically in the presence of FDHF and tried more and more things to make that work, we started to become convinced that this may be indicating a sort of regulatory change in the affinity of the HIC complex for the FDHF, rather than simply some small difference between the two protocols that we hadn't yet nailed down. And so when we looked at this site, we were interested to note that the interaction between FDHF and HIC-B is dominated mostly by hydrophobic interactions with a few hydrogen bonds, but there's an additional interaction between HIC-F subunit and the FDHF. And that happens between this really negatively charged region on FDHF and the very positively charged patch here on HIC-F, and the metal ion is found exactly in the middle of that patch. And so that got us to thinking whether this could play some kind of role in a potential regulatory process that was the reason we kept losing the FDHF. And we thought about that. We were purifying, of course, in the absence of oxygen, but also in the presence of hydrogen. So our tint has 5% hydrogen, and so we expect slightly more reducing conditions. And it made sense to us that if we have a redox active ion in this position, that the reduction of that ion would decrease the overall positive charge there, and therefore decrease the strength of interaction of FDHF with the HIC-F subunit. And we also noted a slight difference in the density for the arginine, for an arginine that's very close to that ion, but it's impossible for us to say whether that is, let's say, caused by a change of the ion, or whether that's just caused by the association of the FDHF in that position. So, but it looks like quite an interesting thing to investigate further, and so we're definitely going to be following up on that. But it's kind of a fun little thing that sort of came that we didn't expect at all. These cysteines are conserved in other formate hydrogen lyase type complexes, so in FHL2, for example, from E. coli, and in other FHLs, but not in complex 1. And not in other hydrogenases. Okay. So now kind of moving on to the nickel ion site, we were interested in thinking about what are the structural aspects that are important for determining the activity of Hy3, or the difference in the activity that we observe for Hy3 relative to other nickel iron hydrogenases. And so the kind of core catalytic cluster looks very similar, so it's entirely consistent, at least at this resolution. So that's about 2.6 angstrom we're sitting at, with what has been described previously for other nickel iron hydrogenases. But what we see, for example, in the proton pathways is slightly different. So I think Sven, for example, and work from Mark Rousset's group also showed the importance of this glutamate on a beta-1, beta-2 loop in accepting a proton via one of the terminally ligating cysteines of the nickel iron cluster. And interestingly enough, in the MBHs, this beta-1, beta-2 loop is a little bit more flexible, and it's homologous to a loop that carries a histidine that's known to be important for binding quinone, and is probably donating one of the protons for quinone reduction. And so it's kind of fascinating to see that role conserved over so many million years of evolution. But what we see in that loop is more flexibility. Sorry, I'm gonna have to go forward and back because I think I got my animations the wrong way around. But what you can see when you look at the beta-1, beta-2 loop is that in the soluble hydrogenases, there are a few more hydrogen bonds that kind of stabilize that. And so it seems to be a bit more rigid, whereas in the MBHs, it's a bit more flexible. And that has also been shown for complex 1. So there are different structures of complex 1 solved under different conditions that give different positions of this beta-1, beta-2 loop. And recent MD simulations that were done by, sorry, I have to look at my notes because I'm a little nervous. These are all things that I knew, but sorry, yeah. So MD simulations done by Vilakaila on the Pyrococcus structure actually found that when they protonated this acidic residue on the beta-1, beta-2 loop, the loop moved closer to the active site, and when they deprotonated, it moved further away. And so we're sort of speculating, and maybe this is a good community to kind of get opinions, but we're speculating that possibly that flexibility, and in particular that protonation dependence, could actually bias the enzyme toward hydrogen production by protonating the active site, which should decrease the probability of hydrogen binding. So that's one potential, let's say, idea of what could make Hy3 so special. The other thing is related to where another proton may move from the active site. So obviously, in addition to this glutamate, there have also been mutational studies done by Rhiannon Evans and Fraser Armstrong looking at this arginine in the canopy. So the arginine aspartate pair are really important for catalysis at the nickel iron site. And there seems to be a reasonably well conserved pathway for protons moving from that arginine. And so what's different between the MBHs and soluble nickel iron hydrogenases is this other residue in the canopy. So that's pretty consistently an aspartate in the soluble, or sorry, in hydrogen oxidizing enzymes. And it's a serine both in the MBHs and in the nickel iron selenium enzymes, which I think people know are not that closely related to the MBHs, but actually much more closely related to the hydrogen oxidizing enzymes, but share with the MBHs an ability to produce hydrogen. So that's a second lead that we think is really worth following up on in terms of understanding what makes Hy3 have these different properties from other enzymes we've looked at carefully. Okay, so how do you get the proton to the glutamate on the beta-1, beta-2 loop? That seems to be a little bit different for MBHs than for soluble hydrogenases. So this is from the work of Ogata and Lupitz, where they looked at at very high resolution at proton pathways toward that glutamate, and the residues on these pathways are not conserved in MBHs. So it doesn't seem to be any of those three pathways for MBHs, and what seems potentially more likely is actually something much closer to what we see with other relatives in the complex 1 superfamily. So the glutamates on this loop cluster, it's beta-1, beta-2, sorry, on the beta-1, beta-2 loop, are basically at the top of a large hydrophilic channel that goes all the way into the membrane subunits. And what you can see here is a K-var analysis of our structure showing where water can fill in. That's lined by a lot of charged and hydrophilic residues. So it seems that it should contain water. We also see a few waters there. And what was interesting for us when we had a look at this, the hydrophilic channel seems to kind of move all the way to this glutamate 138. And that glutamate 138 is then directly opposed to the Hc subunit, to the antiporter-like subunit. So there's no gap between those two subunits. They're nice and close together. And the glutamate 391 on the other side also is important. So we could kind of line up our ideas of where the protons are moving with some mutational studies that were done by Connie Pinske and Frank Sargent, looking at proton conduction through this pathway. And what we found, it took us a little while to figure out where the protons were going, because we started off with homology to complex 1 as a kind of model. But when we looked at the pathway that's been described in the antiporter-like subunits of complex 1, there were several mutations to, for example, this glutamine and that alanine that didn't seem to make sense for us. And we really didn't see a consistent pathway for protons. And that in a way makes sense because the experiments that Connie Pinske and Frank Sargent did had tried mutating a lot of these residues in the Hc and found that they didn't have an impact on in vivo hydrogen production, even though mutation of residues up here did have a large impact on the hydrogen production. And then when we kind of had a bit of a closer look, we actually found a different pathway for protons that's just kind of one helix over, if you will. And when we found that and started looking at it, then we were actually quite convinced that protons should be able to pass through here. And that ended up lining up very nicely also with these mutational data that found an effect of mutating, for example, this glutamate 391 and this aspartate 354 that wouldn't normally be on the pathway for other antiporter-like subunits. So we still don't, I mean, I think the question at this point that everyone asks is, so does it pump protons? We would really, really like to know the answer to that. And we're not quite confident enough to make a statement on it, but to us, it looks very much as though protons have to pass through this pathway in order for FHL to actually produce hydrogen. And so we can't say with total confidence whether that's protons that are passing across the membrane or whether those are substrate protons that are entering through the antiporter-like subunit through this not fully conserved pathway and up into the E channel. So with that, I would just kind of like quickly summarize. So we note that anaerobic purification is very important to both the structure and the function, but that unfortunately under reducing and anaerobic conditions, the FDHF interaction seems to be less strong. We've generated a few structure-based hypotheses related to how the FDHF attachment may be regulated and the basis for the higher hydrogen production activity. And the proton pathways, although they're not entirely consistent with other members of the complex 1 superfamily, do align very nicely now with previously published data from Frank's lab about the proton movement through those pathways. Yeah, thank you for your time. And this is very important. I shouldn't forget this. So I'd like to thank, of course, all the members of my lab, but in particular Ralph, who worked on the project with a lot of dedication, and Rita, the TA in our lab, who also helped a lot, our central electron microscopy facility, who are really excellent, Stella Witt from the Amnas group, who gave us a lot of help in the early days with anaerobic setup, as well as Johan Heider and Gabi Huth at Philipps University Marburg, who did the anaerobic fermentation, and Frank at Newcastle University, Frank Sargent, sorry, who provided us with a strain to begin with, and some nice chats along the way. I'm open for questions.